Hey, let's continue our discussion of volume with some slightly more complicated examples. And our first example is this one. We'd like to find the volume of the solid generated by rotating the region enclosed by the curves y equals x squared and y equals 2x about the x-axis. And the picture looks something like this. And so the region that we're talking about is the region that's shaded in here. And the first thing you really need to know is, where do these two curves intersect? And in this particular case, you might be able to just guess, but we need some technique that will get us the answer in general. The curves intersect where they have the same x and y values, and we're given what the y values are for both of these curves. For any value of x, they are x squared and 2x. And so if we want those y values to be equal to each other for a particular value of x, then we can find where that happens by solving the equation x squared equals 2x. In other words, we set the two equations equal to each other. X squared equals 2x. And that's a quadratic equation. To solve it, you get everything on one side of the equal sign and a 0 on the other. And then you factor and you come up with the fact that these two curves intersect at x equals 0 and at x equals 2. Now we should try to visualize what it looks like when you take this region and rotate it about the x-axis. And within the limits of my drawing ability, you get something that looks something sort of like this. Another trumpet shape pointing out to the right, hollowed out in the middle, but with some thickness, so that blue shaded region getting rotated around leaves some thickness all around the inside of this shape. To try to make it a little more clear and also to come up with a formula for this volume, let's see what would happen if we looked at a thin cross-section of this solid. Well, start with a thin rectangular two-dimensional region like I've got drawn here in green, and then rotate that about the x-axis. And it's a little bit hard to see, but you get this thing that looks like a washer sort of standing up on its edge. Here's a larger view of the same thing just to make it a little bit more clear. And here I've shown the x-axis going through it just to put it in the context of the picture. And it turns out that it's not hard to compute the volume of something of this shape. It's essentially a cylinder with a cylinder cut out the middle of it. As before, the cylinder is on its side. And so we would normally refer to as the height of the cylinder is really the thickness of this washer, and that's delta x, the change in x, or the thickness of the original rectangle that we chose. And then there are two interesting radii. There's an outer radius and an inner radius, and one of them comes from one of the functions involved, one of the curves involved, and the other comes from the other. But before we relate it to the specific problem that we're working on, we can come up with a general formula for the volume of a solid of this shape, something of the shape of a washer. And since what we have is a cylinder cut out of a cylinder, it's the volume of the outer cylinder, so pi times the outer radius squared times h, minus the volume of the part that was cut out, the cylinder pi times the inner radius squared times h. And factoring out the pi and the h, that gets us pi times the outer radius squared minus the inner radius squared times h. That's the volume of a single one of these washers. But as usual, we can approximate the volume of the whole thing by adding up n of these washers, and then get the exact volume of the solid that we're looking at by taking the limit as n goes to infinity, and that limit turns into an integral. And in this context, the h was the delta x, and as you go to infinity, that becomes the dx. And so in general, we've got the volume of some solid of this sort from some point A, some x value A to some x value B, is always pi times the outer radius squared minus the inner radius squared with respect to x. All that's left for this particular problem is to determine what the outer radius is and what the inner radius is. And since we're rotating about the x-axis, the radius is always going to be the distance from the x-axis to the point on the curve. And although it's gotten a little bit crowded and hard to see, hopefully you can see that the outer radius is this red line right here, the distance from there all the way down to the x-axis. And how did we decide where to stop? We stopped when we hit this curve y equals 2x. And so for any given value of x, the y value there is 2x. And so the outer radius, 2x. And similarly, also hard to see, but the inner radius is this distance right here that I've also done in red. It starts at the x-axis and stops when we hit this bottom curve, and the bottom curve there is x squared. And now we're in great shape to compute the volume that we've been looking for. According to the formula, the volume is the integral from 0 to 2, because that's where the shape begins and ends. That's where the region that we are rotating begins and ends at those x values, of pi times the outer radius, which is 2x, all squared, minus the inner radius, which is x squared, all squared, with respect to x. Be a little careful with the algebra. In particular, when you square 2x, you get 2x times 2x, or 4x squared. And it turns into the easiest calculus problem that you've seen in a long time. Probably the hardest thing is adding the two fractions at the end. And I'll let you verify that you get 64 pi over 15 as the answer. Okay, I'll do this one, you do the next one. I've abbreviated a little bit here. What we're doing is finding the volume of the solid generated by rotating the region enclosed by, so I left all that out, the three curves y equals x squared, y equals 0, and x equals 1, and rotating that region about the line y equals 2, as opposed to about the x-axis as we have done thus far. So let's draw a picture. Here we have the curve y equals x squared, more or less, the line x equals 1, and the line y equals 0 is just the x-axis. And so the region we're talking about is this region here. And I was a little off on my scale on the y-axis because we would like those two curves to intersect at the point 1, 1, so I've adjusted that right there. And now we have to try to see what it would look like if we rotate this about the line y equals 2, which is of course a horizontal line passing through y equals 2, as I've drawn here in green. And from the outside, it looks more or less like this, but you have to keep in mind that there's this part carved out from the inside because we've taken this area in light blue down at the bottom that's covered over somewhat now in dark green and rotated it about the line y equals 2 to form this solid. And so the fat parts form some fatter piece of solid, and then it gets, thinner. The thin parts form some thinner piece. Perhaps it will be clearer if we just start talking directly about outer and inner radii. This is some solid that we generated by rotating around the line y equals 2. So y equals 2 is the center of this solid. And so every radius is going to start at y equals 2. And one way you could describe the outer radius is this distance here that I've drawn in red, but that's a more difficult way to describe the outer radius because it's hard to say where you stopped to determine what that length is. Here's a better way to describe the outer radius, is to go down from the center. And regardless of what x value we started at, the distance is the distance from y equals 2 to the x-axis, or the distance from y equals 2 to y equals 0. In other words, the top point on this line segment is the point x2, and the bottom point is the point x0. And the distance between those 2 points is the change in their y values. It's just 2. So what we've just determined is the outer radius is 2. The inner radius, on the other hand, stops when we hit the curve y equals x squared. It's this second red line that I've drawn here, this red line segment. And if you look at the x and y coordinates of the endpoints of that line segment, so different value of x here, but it's some x value between 0 and 1. The coordinates are x2, once again, for the top point, but then the bottom point is x, x squared. The y value for any given value of x is x squared because it's on the line y equals x squared. So that's for that bottom point. And so how far apart are those 2 points? Well, it's once again the change in their y values, which is to say that the inner radius in this case is 2 minus x squared. And now we've done all the hard work. Not that it was so hard, but now we just plug it into our formula. The volume is the integral from 0 to 1, because that's what those are the bounds on the region that we originally rotated about the line y equals 2, of pi times the outer radius, that's 2, squared, so 2 squared, minus the inner radius, 2 minus x squared, all squared, with respect to x. There's a little algebra to do. Make sure that when you're squaring 2 minus x squared, you get all the terms. It's 2 minus x squared times 2 minus x squared. Make sure you're subtracting that entire quantity from the 4. And the details are less interesting. Make sure that you can add the fractions at the end. And in the end, you get 17 pi over 15. Okay, that was the one that I was doing. Here comes the one that you're doing. Same curves, same picture, at least to start. But instead of rotating about the line y equals 2, we'll rotate about the line y equals -1. And so see if you can compute the volume of the solid that you get when you take this region enclosed by y equals x squared, y equals 0, and x equals 1, and rotate it about the line y equals -1. Try to draw the picture, try to compute the volume, pause the video, take a few minutes, and then when you're ready, start it up again. And after you draw in the line y equals -1, which I have in light green there, and then take your best stab at sketching what the shape will look like, the solid that you get when you rotate this region about that line, you get something sort of like this. And now we have to figure out what's the outer radius, what's the inner radius. Well, the outer radius is this distance here that I've just sketched in red. And those two endpoints both have the same x value, so to compute the distance, how long that segment is, you subtract their y values. And the y value of the top point is x squared, and the y value of the bottom point is -1, and so you get that the outer radius is x squared minus -1, or x squared plus 1. Similarly, the inner radius is this second red line segment that I've drawn here, and it's the distance from the line y equals -1 to the x-axis, and the y value's there. Well, at the x-axis, the y value is 0, and at the line y equals -1, the y value is, of course, -1. And so the inner radius is 0 minus -1, or just 1, the distance from the x-axis to the line y equals -1. That was all the hard work figuring out those things, so that now we can just plug it into the formula, and we get that the volume is the integral from 0 to 1 of pi times x squared plus 1 all squared minus 1 squared. And then all that's left is some straightforward calculus and algebra and arithmetic, and you should come up with the answer 13 pi over 15. Okay, if you had any trouble figuring out the outer and the inner radius, which is where people have trouble, don't be afraid to actually take the time to label the xy coordinates of the endpoints, as I just did for the outer radius. The top point there, whatever the x value is, that the coordinates of that point are x squared, and the bottom point there, same x value and a y value of -1. And so the distance between those 2 points is the difference in their y values, x squared minus -1, or x squared plus 1. Okay, that was the second in a series of 3 volume videos. There is, of course, a corresponding homework named, not surprisingly, Volume 2. As usual, do not forget to have fun doing it. Very, very important. And I look forward to seeing you in class. See you then. Bye.